Let's take a look at an example where a rocket accelerates at a rate of 20 meters per second squared during launch. And what we want to do is find out how long it takes the rocket to reach a final velocity of 400 meters per second. We can start by identifying all of the important information that we're given and what we're trying to find. So we're told that the rocket has an acceleration of 20 meters per second squared, and we're also told that the final velocity is going to be 400 meters per second. We can assume that the rocket starts from rest, so the initial velocity is going to be 0 meters per second, and what we're trying to find is the amount of time it takes for the rocket to reach this final velocity of 400 meters per second. Since we're given this acceleration and it's just a constant value, it's not a function that changes in time, we can assume that the acceleration is constant. And that's significant because what we're going to do is derive some equations that only work when the acceleration is constant. To derive these equations, we're going to use the definition of average acceleration, which is the change in velocity over the change in time. And I can write delta v as v final minus v initial, and delta t as t final minus t initial. We're going to simplify things a little bit here, and what I'm going to assume is that the initial time is going to be 0 seconds. And so where I have a t sub 0, we're going to replace that with a 0. Then I'm going to do some quick algebra to say that v minus v0 equals the average acceleration times the time. And I don't need to include that t minus 0 anymore. Finally, I'll add that negative v0 over to the other side so that I get v equals v initial plus the average acceleration times the time. And this is one of the equations that we can use called kinematic equations that when we have something moving with a constant acceleration, we can solve for the velocity. In this example, though, we already have the final velocity, and instead we want to solve for the time. So let me rearrange this kinematic equation to solve for the time, and then we can plug in the values that we have. We know the final velocity is 400 meters per second, the initial velocity was 0 meters per second, and the average acceleration is that constant value that we were given of 20 meters per second squared. So from this kinematic equation, we find that it takes 20 seconds for the rocket to reach 400 meters per second. Now I'm going to derive another kinematic equation, but this time I'm going to use the definition of average velocity instead of average acceleration. But we can do the derivation in a very similar way. So we know that the average velocity is defined as the displacement divided by the interval of time for that displacement to occur. And so the displacement can be written as the final position minus the initial position, and the time interval can be the final time minus the initial time. And just like before, I'm going to say that the initial time is 0 and plug a 0 in for t0. I'll rearrange this and solve for x minus x initial, which is x final minus x initial, and that will be equal to the average velocity times the time. And then I can take that x initial and bring it over to the other side to get the final position equals the initial position plus the average velocity times the time. And so this is another kinematic equation that we can use. But this assumes that the object that's moving is moving with a constant velocity and not accelerating. If the velocity changes in time, we're going to have to account for that. Here I've rewritten the equation that we just derived, and then I'm also going to describe the average velocity by actually calculating a mathematical mean. If I take an initial velocity and add it to a final velocity and then divide by 2, that's just the mean or the average of those two values. Now let's write the kinematic equation we derived before from the average acceleration, where the final velocity equals the initial velocity plus the acceleration times the time. And then I'm going to manipulate this equation by doing whatever I do to the left side, I do to the right side, but I'm going to do it to make it look like this average velocity. So the first thing I'm going to do is I'm going to add v initial to both sides of the equation. Then I'm going to divide both sides of this equation by 2. Now it's clear that the left-hand side of this equation looks just like the v average that we defined earlier, the average velocity based on the mathematical mean of 2 values. And that means that this side of the equation must also be equal to v average. So let's plug it into the displacement equation where we have v average. So we have the final position equals the initial position plus v average, which we can now write as v initial plus 1/2 at, and all of that times the time. Again, what I did was I took this, which is equal to v average, and substituted it directly into that displacement equation. As a last step, we can distribute the t to both terms to get the final position equals the initial position plus the initial velocity times the time plus 1/2 times the acceleration times time squared. And this is another kinematic equation that we use all the time whenever we have motion that has a constant acceleration. Okay, we're going to derive another one. And again, we're going to use what we already have. So we have this velocity equation that we derived from the average acceleration. And I can take it and rearrange it to solve for time, kind of like we did in that example problem. What we're going to do in this derivation is take this position equation, x equals x initial plus v average times t, and we're going to take this value for v average, the one that we just calculate the mathematical mean between initial and final velocity, we're going to plug that in here at v average, and then we're going to take this derived value for the time and we're going to plug it in here. When we make these two substitutions, it's going to look like this. The rest of this derivation is just algebra, and what you'll end up with in the end is the final velocity squared equals the initial velocity squared plus 2 times the acceleration times the displacement. And so here we have another kinematic equation that describes the motion of a particle that moves with a constant acceleration. What's special about this one is it doesn't have time in it, and so sometimes it can be useful if you don't know anything about the time. So here are the one-dimensional kinematic equations for motion with a constant acceleration. You're going to practice using these in a bunch of problems to follow this video.